we saw that according to Onsagar, if both the processes occur simultaneously near equilibrium, the flows and forces are related by this phenomenological equations. That means J1 will be equal to L11 x1 plus L12 x2, and similarly J2 will be equal to L21 x1 plus L22 x2, where this L11, this is simply the thermal conductivity, because we have taken a case where both temperature gradient as well as mass flow was there, or matter flow was there. So this L1 is simply the thermal conductivity coefficient. This L11 basically relates J1 with x1, and L22 is simply the diffusion coefficient. And relates J2 with x2. These coefficients, that means L11 and L22, they are positive. L11 and L22, they have positive values. Now the cross coefficients, which were represented by L21 and L12, they basically describe the interface or interference, you can say interference or coupling of the two irreversible processes, these two which we are discussing, two irreversible processes. And these L121 or L12, or you can say 1 and 2, these are called as drag coefficients. and can be of either sign. That means positive or negative. Or these cross coefficients, we can say they are basically so. Here this L12, in this example we have represented it as heat flow. Arising from simply temperature gradient. And L21 represents simply flow of matter, and this arises from concentration gradient. So in general, these equations, that means J1 and J2, can be written as that means we can simply write a general equation. Ji will be equal to Lii xi plus Lik xk and Jk is equal to Lki xi plus Lkk xk. That means simply what we have written a general equation of the first equation was J is equal to L of x. This was our equation number first, and the second equation was J1 is equal to L11 x1 plus L12 x2. This was our equation number second, and J2 was equal to L21 x1 plus L22 x2. So this was our equation number third. So you can see here this J11, in place of J1 we have represented it as in general Ji. So here it is L11, we have represented a Lii. That means this I will be having the same values. Similarly, rest equation is formed from these two equations 2 and 3. These are basically phenomenological equations, so we can form a general expression here. This is our general case. So here the coefficients Lik are these coefficients Lik, Lki, or you can write it as Lki, this one, or and this Lii and Lkk, that means these coefficients Lkk, Lik, Lii, Lki. These are simply called as phenomenological coefficients. But out of these four, this Lii having the same value here and Lkk, these are called as ordinary or you can say direct coefficients. While the Lik and Lki, these are simply referred to as cross coefficients. These Lii and Lkk, these are also called as, we can call them as primary, also primary phenomenological coefficients. And while these cross coefficients, these are called as Onsagar's phenomenological coefficients. So we have basically defined various coefficients, this Lik, Lki, Lii and Lkk. Okay. So Onsagar basically showed that with a proper choice of fluxes and forces, Lik, you have to remember this, it is very very important, Lik is equal to Lki. That means these cross coefficients are basically equal. This was actually shown by Onsagar. So if by proper choice I mean, suppose that this flux is basically the function of with respect to dt, where f is simply a state function equation, or you can say simply state function. So this equation 6, this is called the Onsagar reciprocal relation. Or this is also called as reciprocity relation. Or you can, if you have many relation, then so the very important point you have to remember here is that the derivation basically of the Onsagar equations is based on the principle of microscopic reversibility. And this point is the application basically of statistical mechanics, particularly to systems which are close to equilibrium. Okay, thank you.